I welcome to all on the course of Refrigeration and Air Conditioning. Today we are going to solve some numerical problem based upon the vapor compression cycle. Let's start. The temperature limit of an ammonia refrigerating system are 25 degrees Celsius and minus 10 degrees Celsius. If the gas is dry at the end of the compression, calculate the coefficient performance of the cycle, assuming no undercooling of liquid ammonia. And here the properties of the ammonia given in the question. Here I want to say some points. If in the question the refrigeration table is given, means properties is given in the question, mandatory you have to use the data given in the question. If question is silent about the properties of that refrigerant, then we have to use the refrigerant table. So here fortunately data is given in the question, so you have to use this data. Second thing, whenever you are going to solve the problem, first you have to confirm this problem belongs to which type. In the theory class, we have completed the 5 types of vapor compression cycle. Then here you have to confirm this problem belongs to which type. Then we will draw the diagram accordingly the types of vapor compression cycle. For that reason, first you have to know this problem belongs to which type. So here you observe the gas is dry at the end of the compression. Gas is dry end of the compression means the end of the compression, that is the state 2. At the state 2 lies on the dry saturated line. So this problem belongs to type 1, that is vapor compression cycle. After compression, it lies on the dry saturated point. So then you come to the refrigerant properties. How to write the refrigerant properties mathematically? Enthalpy question is given the temperature limit 25 degrees Celsius and minus 5 degrees Celsius. Accordingly, the liquid heat, latent heat and liquid entropy is given. All of you know the liquid heat means HF is given, latent heat means HF is given, and liquid entropy means SF data is given. At 25 degrees Celsius, state 2 and the state 3 is lying, and at minus 10 degrees Celsius, state 1 and the state 4 lies. So we can write T2 is equal to T3 25 degrees Celsius plus you have to convert degrees Celsius to Kelvin, then 25 plus 273, that will come 298 Kelvin. T1 is equal to T4 minus 10 degrees Celsius, then R 273, that will come 263 Kelvin. This is liquid heat means HF is given, so we can write HF3 is equal to H4. Why it is equal? This is a isoenthalpy expansion process. Enthalpy is constant. For that reason, you are writing HF3 is equal to H4 that is 298.9 kilojoule per kg. Correspondingly, 25 degrees Celsius latent heat is given. Then we can write HFG2 is equal to 1166.94 kilojoule per kg. Liquid entropy SF2 is given 1.1242 kilojoule per kg Kelvin. So this is about the 25 degrees Celsius. Now we are coming the lower temperature limit. Lower temperature limit minus 10 degrees Celsius, state 1 and the state 4 is lies. So we can write HF1 is equal to 135.37 kilojoule per kg. Latent heat means HFG correspondingly minus 10 degrees Celsius. Then minus 10 degrees Celsius state 1 and state 4 is lies. Then we can write HFG1 is equal to 1297.68 kilojoule per kg. Then liquid entropy is given minus 10 degrees Celsius. That is, we can write SF1 is equal to 0.5443 kilojoule per kg Kelvin. These are the data you are taken from the refrigeration table given in the question. So, now we are going to the diagram. In the diagram, you observe the lower temperature limit is the 263 and the higher temperature limit 298 Kelvin. And question is given after compression it is lies on the dry saturated line. All of you know that this is the saturated liquid line and this is the saturated vapor line, and under this saturated liquid line and saturated vapor line, that is dome, the dome is the HFG or FG line. You can write this is the saturated liquid line HF or saturated liquid line, this is the saturated vapor line. Now you observe, all of you know the process 4 to 1 condensation process, 1 to 2 isoentropy compression process, 2 to 3 is the condensation process, and 3 to 4 is the expansion process, and 4 to 1 is the evaporation process. This is the TS plot, and the PS plot also same process. 4 to 1 evaporation process, 1 to 2 compression process. Due to the compression process, enthalpy is increasing, and 2 to 3 is the condensation process, and 3 to 4 is the isoenthalpy expansion process. Now you observe, due to the isoenthalpy process, H3 is lies, the state 3 lies on the saturated vapor line. So we can write H3 is equal to HF3 is equal to H4. And this is the HF1. HF1. This much only HF1. And this is the H1. So H1 is not equal to HF1. The 2 is lies on the saturated vapor line. We can write H2 or HG2. So let's come to solve the problem. So in this question, the 1 is lies on the liquid plus vapor zone. Then you have to calculate dryness fraction at the state point 1, that is X1. Then S1 is equal to SF1 plus X1 HFG1 by T1. SF1 is given, that is 0.5443 plus X1, that is unknown. HFG given 1297.68 and temperature is given 263. And if you solve, then you will get 0.5443 plus 4.934 into H1. Then similarly we will calculate the entropy at the state point 2. The 2 lies on the saturated vapor line, so dryness fraction is 1. So we can write S2 is equal to SF2 plus HFG2 by T2. So SF2 is given 0.5443 plus HFG2 is given 1166.94 and T2 is given 298. So finally we will get S2 is equal to 5.04 kilojoule per kg Kelvin. All of you know that the S1 is equal to S2. So we can equate the two equations. 0.5443 plus 4.934 x1 is equal to 5.04. If one unknown, one equation, so easily you can calculate the x1. So x1 is equal to 5.04 minus 0.5443 by 4.93. So you will get 0.91. So if you know the x1, so easily one calculate the enthalpy. Here you remember another point. When you are going to solve the vapor compression problem, so first you have to calculate the enthalpy at the each state point. Because when you are going to calculate the COP, the enthalpy is required at the state 1 and the state 4 and the state 2. So first here you are calculating the enthalpy at the H1, state 1. So H1 is equal to HF1 plus X1 into HFG1. HF1 is given 135.37, X1 is given 0.91 and HFG1 given 1297.68. So if you calculate, you will get the 1316.26 kilojoule per kg. Like that, we can calculate the enthalpy at the state 2. So H2 is equal to HF2 plus HFG2 because the dryness fraction is here is 1. So you will get 298.9 plus 1166.94. If you solve it, you will get finally 1465.84 kilojoule per kg. So first our aim to calculate the COP of the cycle. The COP of the cycle is the refrigerating effect by work done. The refrigerating effect, that is H1 minus H4, we can write H1 minus HF3 by the work done, that is H2 minus H1. H1 just now you are calculated, that is 1316.26 minus HF3 298.9 by H2 minus H1, H2 you are calculated 1465.84 minus H1 1316.26. So if you calculate this, you will get the COP is equal to 6.8. So you are observed here, the COP is always greater than 1 and the efficiency is always less than 1 unit, 90%, 70%, but COP is always greater than 1, and here also you are getting the 6.8. So today you are completed the first problem. Next class I will solve another numerical problem. Thank you.